Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Last time we started to talk about adversarial search and adversarial games, and inshallah we'll talk more about how to model this kind of games and how to actually play this type of games. I think this is exactly where we stopped last time. We were talking about types of games. We said that there are deterministic games and there are stochastic games. Also, there are the number of players is another dimension of variability here. Some games have one player, two players, or even more players. I think we also mentioned what we call zero-sum games. In zero-sum games, the players are playing against each other. So if one wins, the other loses. And that's why we call it zero-sum, because the gain of one player is the opposite of the other player. So like the negative of it. So that's why the sum will be zero, and that's why we call it zero-sum games. We also mentioned that there are types of games where we have perfect information about the states, where we see actually what the opponent is doing, and there are other games for which we don't see the full picture of the states. And what we are aiming for here for the algorithms to play this game is to provide or to reach what we call a strategy or a policy. The strategy or a policy will recommend, given a specific state, will recommend a move from that state. And that's completely different, of course, from regular planning. In regular planning, we have a full plan from the start state to the end state, and it's a sequence of actions. Here, we just need, for every state, we just need a strategy to tell me what is the next state. So we'll focus on deterministic games for now. We can model deterministic games as follows. We have a set of states, starting at a start state, of course, is 0. We have n players, and the n players will usually take turns. Okay, so they will not play simultaneously. They will take turns. And we have also actions, and the actions, of course, depend on the player and the state. We have what we call transition function that will tell us, given a state and an action, what will be the next state. We have a terminal test to tell us or to determine if the game has ended or not, given a specific state. And we also have what we call utilities. Okay, so at the end of the game, for every state that we call a terminal state, the state where the terminal test will be satisfied, the state by which the game will end, there will be a utility for each player. And the utility for each player is the gain that the player got from the entire game. Okay, so that's like the reward of the player at the end, or the number of points that the player got. Of course, that depends on the specific game. And again, the solution for a player is a policy that, given a state, will tell us what will be the action, the best action for that state, or moving from that state. Sorry. So this is just to contrast again the zero-sum games versus the general games. In zero-sum games, agents have opposite utilities, so opposite in values of the outcomes of the game, and that's why actually we would just keep one value if we assume that we have two players. Just keeping track of one value will be enough, because the other one would be the negative of it. Remember, the sum of it is 0. So if the value for one player is 10, then the value of the other player will be minus 10. Okay, so we'll just keep one, and we'll just keep the one that we will maximize, assuming that this is the agent that we control, and for the opponent it would be the opposite value. And for the opponent should minimize that value. On the other hand, the general games, the agents can have completely independent utilities, and they might cooperate and they might compete. It depends on the game, but sometimes in a game, both might have positive values. So it doesn't have to be zero sum. And inshallah later in the course we might talk about non-zero sum games, but we'll focus for now on zero sum. So we'll start now talking about what we call adversarial search. We'll start with a very simple example in the beginning. We assume that we just have one player, just single agent 3. So we'll have just this very simple game where Pac-Man is here, and Pac-Man wants to get to eat this food item. So what are the possible actions in the search tree? Well, Pac-Man can go left or can go right, and that's the state if he goes left, and that's if he goes right. Then from each of these states we have also 2 actions, left or right. So for example, for this state, this is a terminal state, right? Because we ended the game by eating the dot. So the value here for a terminal state, we can have a value, which is the utility of the game when the game ends at that state. Assuming in Pac-Man that every move is -1 point, and when Pac-Man eats the dot, he will get 10 points. So -1 here, -1 here, 10 here. So the value of this will be 8. So that's the value of that state. Okay, which means the value of the agent that we control if we reached that state. Now, of course, this is a terminal node. The game ended here, but the game didn't end here, so we can go down further in the tree if we want, and we'll find that this is maybe a huge subtree, depending on the specific game. At the end, we'll have values. As we said, this is 8, and you might have also values here for the gain or the utility of the game for Pac-Man. So this is 6, this is 4, this is 6, this is 2, 0, 2, and so on. So for all the terminal states, we will have the value. Okay, just to model this formally, let's say that the value of the state is the best achievable outcome from that state. So, for example, here, we said that for terminal, the value of the state is known already by the game. So this is known already to us by the rules of the game. Now, let's think about the value of that state. So every state will have a value, by the way. For terminal, it is straightforward. It is the value that is given by the rules of the game when the game ends. Knowing here that the movement is -1 and eating the dot is 10, then this will be 8. Now, if we think about the value of that state, if we are in that state and we are controlling Pac-Man, what should we do? Knowing that here we will reach 8, and here we will reach 6, and here we will reach 4. That's all the possible gains or values that we can reach. Of course, Pac-Man, since we are assuming that he is an optimal agent, it will try to maximize its gain. So the gain of this state is the maximum achievable by the children. What is the maximum achievable here? Of course, it's just one state, it is 8. What is the maximum achievable here? We have 4 here and 6 here. So the maximum achievable here, the best that Pac-Man can do going from that state, is to gain 6 points. So that's the value of that state. Okay, now moving one step up, what will be the value of that state? First, what is the meaning of that question? The value of that state means that what is the gain, what is the best gain I can get moving or starting the game from that state or moving from that state. If the value of this state is 6 and the value of this state is 8, and of course Pac-Man wants to maximize its gain, then the Pac-Man will choose to go this way, which means that the value of that state, of this state, will be 8. Similarly, we can do the same on the other branch. Here, the value of that state is, assuming that we have all the values here, 2 and 6, so the value of this state will be 6. The value of this state among 2 and 0, we are maximizing, of course, so the value of that state is 2. That means that the value of this state is the maximum of 2 and 6, which will be 6. Now, what is the value of the root of the tree? We are between 6 and 8, we are maximizing, of course, so the value here will be 8. we call this the value of the game, of the entire game. Of course, this is the value of that state, but since this state is the root, is the starting state of the game, we call this the value of the game. So the value of this game is 8. So generally, the value of a state is the best achievable outcome or utility from that state. If the state is terminal, so the value is known already from the game. If the state is non-terminal, if it's non-terminal, then the value of the state is the maximum value of the children. Okay? So this is the definition of a value of a state. We have two cases, either terminal, and that will be determined by the game, or non-terminal, and we have to move bottom up to get these values. The value of a non-terminal state, it's the maximum value among the values of the children, and of course so on. So you have to move bottom up to get these values. At the very top of the search tree is the start state, which will give us the value of the entire game. So that means that if that game is played by Pac-Man, then Pac-Man would choose to move this way and then this way to get this 8. That's the best that Pac-Man can do for this game. Why is that? Because of that these values are of course less than 8, and this is just one player game, so of course Pac-Man will maximize at every step. So this is just for simple one player game. We are controlling everything here, but things will change if we have adversarial game 3. If the game that we are playing is adversarial, we have two opponents that are playing against each other. Before we start that, let me ask you if you have any question on this. Yes, Mahmoud. This one? Because this one is 8, and this one is 8 because this one is 8 and this one is 6. We are maximizing here, right? This is just one player game. So at every step, the agent is trying to maximize its value. It's trying to maximize its gain. Oh no, where's the yeah. Well, this is how we got the values of the terminals. Yes, this is because this is -1, this is -1, and eating is 10, so it's 8. But I'm talking now about the value of the state. If it's terminal, yes, we get it from the rules of the game. But if it's not terminal, we have to get it from the values of the children. Is that clear, Mahmoud, or still not clear? Exactly. Yes, exactly. Yes. Okay. But to do that, we have to move bottom up. Okay. Is that clear now, Mahmoud? Okay. You're welcome. Any other questions? So everything is clear up to this point? Because things will be more complicated when we get to adversarial game. We have two agents then. Okay, so let me move on to adversarial game 3s. Now we have two agents. We have Pac-Man playing against the ghost here. Okay, so of course this is a simple game. So if we assume that that we are taking turns here and Pac-Man will start first, so Pac-Man has two possible movements, either to go left or to go right. Okay, and again from now this is the turn of the ghost. So the ghost is from this state either going left or right, and from that state also going from left to right. So we'll have these two states here and these two states here, and so on. So we can continue the search tree, the game tree, until we end the game. Okay, so for some nodes, this is just some of the values, some of them, not total, okay, but few of them. So this is +8, this is -20, +4, -10, and so on. What are these values? These are the utilities at the terminal nodes. So at some point here, this state, okay, is a terminal node, which means that the game will end here, and the value of the game will be +8. Here, the value of the game, if we ended at that state, will be -10. That means that the ghost won in that game, of course, because because it's positive value for the ghost and the negative value for Pac-Man. Okay, so we can build that tree that might be huge based on the game. Okay, and at the terminal again, the values are determined by the rules of the game, and then if we want to get the value of the game, we move up. But let's now see what will be the values of the non-terminal nodes. And to do that, we will do that on just a simple game, just to make sure that you understand the concept, but of course it can be applied on bigger games. So let's now focus on that simple game. In that simple game, we only have two movements. One by Pac-Man, and the first one will be by Pac-Man, and the second one will be by the ghost. Okay, so just a small tree, and let's think together how we can get the values of the states. Now, for this one, so the terminals, of course, we know the values, okay, based on the rules of the game. So the value here is +8, -10, -5, -8. So the best value, it seems like this is the best state that Pac-Man can reach, right? +8. So maybe Pac-Man will be tempted to go right here, because that's the only way to get this state, right? Is to go right, because remember, Pac-Man controls this state, and the ghost controls that state. So Pac-Man might be tempted to go right, hoping that it can get +8. But this state now is controlled by the ghost, right? So if the ghost reaches that state, the ghost is trying to minimize the value of Pac-Man. Okay, so of course the best for the ghost at that point is to move left. Okay, and thus the game will end with -10. So the value of that state actually is not maximizing as we did before. We were maximizing because everything was controlled by Pac-Man. But here, that state is controlled by the ghost. So this is called min state. We are actually minimizing the value at that state. So instead of maximizing the value across the children, this state, since it is controlled by the ghost will minimize the gain. Remember, this value is the gain of Pac-Man. The opposite of it is the gain of the ghost. So we are minimizing this value, which means that the value of that state will not be +8, it will be -10 actually. Okay, similarly here, if we are in that state, we will have to, because this is controlled by the ghost again, remember this tier is completely controlled by the ghost, this tier is controlled by Pac-Man. So for that state, which is controlled by the ghost, the best is to move left, of course, because we are minimizing again here. So that tier is for the ghost. So the value of that state will not be -5, it will be -8. Now moving up, the value of that state, because this is controlled by Pac-Man, by our agent, then we are maximizing. So this is max here. Okay, so we maximize between -8 and -10. So what is the maximum of -8 and -10? Of course, it is -8. Okay, so now this is the value of the game. So the game, if it's played by two optimal players, will not reach that state at all. It's not +8. It is -8. And why is that? Because Pac-Man will choose to go this way, and then the ghost will choose to go this way. And the game will end based on the rules of the game here. Just one turn for Pac-Man and one turn for the ghost. It will end by -8. So this -8 means that the game will go this way. Pac-Man will go this way, and then the ghost will go this way. And that's the best that each of Pac-Man and the ghost can reach. Pac-Man will not be able to get this. Okay? Any questions on this? Because this is very important to understand. Is that clear? Saad? Yes. Okay, simple. What else? Any other questions? Abdurrahman? Which value? Okay, it depends. Yes. These ones? No, these are given to us. The +8 and -10 here. These are given to us by the game. Don't worry about them. Okay. Okay. Yusuf. Wa alaikum assalam wa rahmatullahi wa barakatuh, Yusuf. How are you? Okay. Yes, yes, I answered this already. Yes, that's given by the game. Okay, I cannot claim that I understood the question 100%, but let me try. I think you are saying, how will they choose their actions if they know that if each one is knowing that the other is optimal? Is that your question? Okay, for that question, that depends on the rule of the game. So because this game in front of us is just simple, we assume that we have just two turns, one by by Pac-Man first, and then the other by the ghost, and that's it. Okay, that will be determined by the rules of the game. Okay, so that's the last question. Again, for the previous question, did you ever play a game with a smart person? Did you play or not play, or you said, "Oh, okay, no, you are smart, then I will not play with you"? You did play, right? Okay. So every game, of course, يعني, when we say smart here, it's a bit different from optimal here. Okay, because smart might also make mistakes sometimes, but optimal here means that it will not make any mistake. Okay, we assume that. So and we will relax that later, inshallah. Not today, but we'll relax it later. But assuming that he is optimal, some games you might be able to win, okay, and some are others. Yeah, for example, this game, it seems like you will not win, right? And you know, the best you can do is to lose just 8 points instead of 10. Okay, but other games you might have a chance to win. There might be some states that are good for you and very bad for the other player. Okay, so depending on the game, that depends completely on the game. Okay, you're welcome. Other questions? Okay, but it's very important for me to understand that this is called Minimax values. So we are not always maximizing. We are not playing alone here. It's two-player games. So what I'm doing, the other agent is trying to working against it. Okay, so that's why it's called minimax. We are maximizing at one tier of the tree, and we are minimizing at the other tier. So again, the terminal states, the values will be known, and for the states under the opponent, the values will be the minimum, okay, across the successors, which are the children. And if the non-terminal state is under the agent control, then we are maximizing. Here, this is under the opponent control. That's why we are minimizing. and if it's under the agent control like this one, we are maximizing. Now I think everyone is familiar with the Tic-Tac-Toe or XO, as we say it sometimes. I think everyone played that game before, and now you can actually think of the game tree for Tic-Tac-Toe. It's just if you don't know it, it's a board of 9 places, and each player has a turn, either writing X or O in one of the empty positions, and the winner is the first player to get 3 in a row, either horizontally or vertically or even diagonally. Now, if you think about this game, and you built the entire tree trying to see what will be the value of the game. Now I think you understand what we mean by the value of the game. The value of the game is the value that the game will end up with if the 2 players are optimal. Now let me ask you, before we do this, I think you played XO many times before, or many of you did that. What is the value of the game if we started the game between 2 optimal players? Anyone? Abdurrahman, seems like you played a lot. Ta'adul, okay. Draw. Yes, so I forgot actually to say that there are 3 possible outcomes of this game. Either the first, the agent will win, which would be +1, like this case, we have 3 X's here. Or the opponent will win, like this case. Okay, so this will be -1, or draw. No one will win. We couldn't get any 3 in a row, so that will be 0. So among these 3 outcomes, Abdurrahman think that the value of the game, which is the value of this state, is draw, which means 0. And this is actually true. If you did this tree, of course this is kind of huge tree, 9, then 9 square, and 9 to the power 3, and so on until the end. If you build that tree and you move bottom up, you will find that the value of the root of the tree is 0. That's the best that a player can get playing against an optimal player. And we all know that if we are both smart players here, or optimal players, it will be a draw. No one will win. Okay, and that's what we mean by the game being solved. Remember last lecture when I said that chess as a game is solved by AI. Solved means that given a state, we know we can control the value of that game. Okay, so for that game we know that if we started with empty board like that, 2 optimal players are playing, the game will be a draw. Okay, and that's what we mean by being solved. Now I want one to get the value of that game with me. Anyone? Yes, you are right, Yusuf. I think I meant checker. Sorry, not chess. Checker. Thank you. Anyone wants to do this with me, Abdurrahman? So what would be the value of that game, Abdurrahman? Okay, so that will be 5 here, 2 to the right. Okay, very good. So Abdurrahman, stay with me please. Now that the value of the game is 5, if we played that game, what will happen? What are the actions that the players will do? No, that's a general game. Let's say that this player, the max player, let's call them the max player and the min player, okay? So the max player can go left or right, and the min player can go left or right. Tell me what will happen if you played that game. Assuming that both players are optimal, of course. طيب, Abdurrahman, I understand, and this is exactly what you did to get the value of the game, right? But what I wanted to say that if you got this value here, okay, that means that this player, that means that this player will always choose to go right. Okay, and then because this is 5, and this is 5 because of this 5, right? Yeah, this 5 is because of this 5. Okay, so that's why the max player will go to the right. Now this 5 is because of this 5, so the min player will go to the left. So this is, yes, so this is exactly what will happen in that game if we played it between two optimal players. The first player will go will go right, and then the second player will go left, and the game will end with a value of 5. Okay, is that clear, Abdurrahman and everyone? Okay, alhamdulillah, Abdurrahman, I managed to make it understandable. Okay, any questions from anyone? To me, this is very fun, by the way. I hope that you are also having fun with this, and we'll have more fun, inshallah, with the project. Okay, any questions? Type. Okay, so this is what we call terminal values, and as I said, this is part of the game. They will be known, and the minimax are computed recursively. Okay, we'll talk about this concept very soon. Okay, so the values are 5 and 2 here and 5 here. Now let's talk about the implementation of this. So we know how to build this tree, and building that tree means that we will get the value of the game and from the bottom up, and getting the value of the game means that we will know the decisions that every player will make. Okay, so as we said, this player eventually, if that's 5, then that means that this player will make this decision, and then this player will make this decision. Okay, in terms of implementation, we'll have to have at least two functions, right? One for the maximum value, for maximizing, for one player, for the agent, for our agent, and the other for the opponent player. So for the agent, it will be max value. So the value of the state will be initialized to a very small value, minus infinity, and then it will try to maximize the values given from all the successors state. So for every successor state, it will call min value of the successor. Why is that? Simply because we are assuming turns, right? Every player is taking a turn. So if I am a max agent, then of course my children will be min agent, will be controlled by the minimum, by the other agent. Okay, so we'll have to call the min value for the successor, and the min value will be similar function. Okay, but instead of maximizing here, we will minimize the value of the successors. Okay, and again, the successors of the min agent are max agents, so we'll have to call the max value. So actually, this function is calling this function for the successors, and this function is calling that function for the successors. And this is, as it's very clear, this is recursive. Okay, so we'll keep calling the children, okay, until we should reach a base case. So the base case is not here, so we need a base case now. So that's not enough. These two functions are not enough. We have to reach a base case. What is the base case here? These are the terminal nodes. Okay, so we have to have a dispatch function that will check first the base case, and then it will check if I am a max agent, then I will call the max value. If I am a min agent, I will call the min value function. Okay, so here, this is now the actual function that I will call in the beginning. Actually, I will call it for every state. If it's terminal, then it will return the state's utility. This is given by the game. If the agent is maximum, it will return the value returned by the max value function. And if it's minimum, it will return the value of the min value function. What are the max and min values functions? They are very similar to the ones that we saw in the previous slide, except that here, instead of saying main value, I will just call this this function because I have to check the base case. Okay, so every time I will call this value function. Okay, so this value function is called from everywhere, and based on the type of that state, whether it's controlled by the agent or the other opponent, or it's a terminal, I will decide. I will return a value. If it's terminal, I will return the value that is the utility of the state that's given by the game. If I am max, I will return the max value of the state, which in return will call value for all the children, and the other way if I am a main agent. So this is recursive, and this is, as we will see very soon, this is very similar to a search algorithm that we already studied. But this is the implementation of the Minimax algorithm. Now let's see how that will work in reality at runtime. If we run this, how it will work. So assuming that we'll start with a max state, this will run exactly like DFS. Remember what is DFS? Depth first search. We have to go to the terminal state and then go up, right? We said that we have to get the values of the states bottom up. So to go to the bottom and then up again, this is exactly what we do in DFS. So at the root of the search tree, we start, and that state, since it is not terminal, it will call the value of the children. So it will start with the first child. Now this child is minimum, so it will call the value of its child until we reach a terminal. Okay, so the child for this one is a terminal, and it has a value 3. So that means that this child will pass back 3 to the parent, to its parent. So now the value of its parent will be 3. Then, as in DFS, the parent will call the value for the second child, which here is a terminal, so it will pass back 12 to the parent. So now this parent is minimum, is main agent, so this state is controlled by the main agent, so it is trying to minimize. So the value of now of that state will not change by this 12. It will stay 3. Now we go to the third child. The third child is 8. Again, 8 is passed back. It's not less than 3, so the value will stay 3. Now we are done with the children of that state. What will happen? DFS, right? We go back to the parent. So this agent, this state, will return back 3 to the parent. So now the value of the parent will be 3. And now the parent, after calling this, khalas, this is done. Now it will call the second child. The second child is not terminal, so we'll do the same thing. We'll call the first child of it, terminal, will pass back 2. So now the value of this is 2. Second child is 4. It will not change this 2. 6 also will not change this 2. So the value of that, and we are done with the children here, all of them. So the value of that state is 2 and will be passed back to the parent. Now the parent has to change the value. Oh, sorry. Actually, no. The parent is maximizing, so we should not change 3. It will stay 3 as it is. Now the parent will call the third child, and so on. So the third child will start with 14. This will be 14. Then 5. Now this has to change, right? Because this is minimum. So this will have to be 5. Now this is, it will get 2. This will have to change again to 2. Now 2 will be passed back. Okay, so this is 2. Now we have 3 here. This is 2. We are maximizing, so that will not change. And we are done because that's the last child. Then this will be the value of the game. That will be the value of that state, which is the value of the game. So the value of that game is 3, which means that this agent, let me change the color now. That means that this agent will take this decision, and then this agent, because this is 3 and that's 3, it will take this decision. So the game will end up here. Okay? So this is what happens in runtime. What are we doing in the runtime? We are evaluating the states. We want to get the state of the root. So recursively, the root state will call the state function or the value function for the child states, and so on. Okay, when that happens recursively and at runtime, it is exactly like doing DFS in the search tree. Any questions about that? Questions? Everything is clear? Okay. Now let's think about this tree, and I want someone of you to tell me what will be the value of this game. Someone other than Abdurrahman. Abdurrahman, you did it last time. Someone else. Should I call names here? Islam, where is Islam? Are you with us, Islam? Islam? Okay, Mustafa Mahmoud. Okay, Mustafa, what could be the value of this game? Okay. Very good. Okay, thank you. So the value of that game is 10. So Mustafa, please, okay, stay with me. Sorry. Now, since the value of this game is 10, what will be the actions of the players? Mustafa. So this player will take the left side. Okay. Yeah, okay. Then this player. Both are the same, right? Doesn't matter. Yeah, any one of them, just for a change that we'll just choose this. Okay, so the game either will go this way and this way, or this way and that way. It doesn't matter. In both, the value of the game will be 10. Thanks, Mustafa. Now, looking at this game, this game tree, the max agent might be tempted to get this 100, and you see here the 4 terminal nodes, 10, 10, 900. Okay, so 100 is tempting here really. How can we get this 100? Is there a chance that we can get this 100? Any thoughts? Is it possible to get this 100? Hamza. Yes, if we are playing against a perfect player, then we will not be able to get this 100. Okay, because if we choose this path, then of course because the other agent is perfect, it will choose to go this way. So we will never get this 100. But what if we are not playing against a perfect player? Maybe we'll take our chance, right? Sometimes we play against not very smart players, right? Maybe our little son or daughter or brother or sister. Sometimes we are maybe smarter than them. We may have a chance, okay? So we might go this way, and the other player maybe by mistake can go this way. Okay, so that's a big difference. There's a big difference, and of course in that case we'll end up getting 100 instead of 10 here. This is that shows the big difference between playing and thinking about playing a perfect player and non-perfect player. If I know that the player against me is perfect, then I will have to choose this path. Okay? If I know that the player against me is not perfect, then there is a chance that if I go this way, I might get here. And even if I get here, I will not lose much from 10, right? So and 9, it's not very far from 10, but there is a chance to get 100. So there is a big difference between these two cases. It's the difference between playing with optimal player like this one or non-optimal player like this one. That's naive player, maybe playing tic-tac-toe for the first time. Let me show you a demo for these two cases again with Pac-Man. So here is the critical situation for Pac-Man. Pac-Man is between two ghosts here and far from the food items. And again, the same rules here. If I move, I will lose points, and if I move more, I will lose more points, and if I get the food item, I will get positive points. So what should be the optimal solution here for Pac-Man? If I know that the opponents are optimal, the opponents here, the ghosts, are optimal, what should be the best solution? What should I do now, Abdurrahman? So you think that it will go left. Okay, but type. Okay. Okay. Okay, type. I saw Faisal also raising hand. Faisal, do you have other solution? Okay. Just a second. Why the blue will go down? It's optimal, ghost. Yes, up or down here, but he's optimal, right? So why should it goes down? What should it go down if it's optimal? Oh no. The goal of the ghost is always to kill Pac-Man. Okay, I can't. Pac-Man cannot. There is no choice to not to move. It's either left or right. Very good. Very good. So that. So is it better? Is it better to spend more time here? Yes. Okay. Very good. Okay, so this is like suiciding here, right? So the optimal solution here is to go right, not left. And why is that? Because if I go right, I will be killed in one more step, which means that I will lose just 1 point or 10 points based on the rule of the game. Let's say 1 point only. But if I go left, I will spend more time and I will lose more points. I will be killed eventually in both ways. And eventually I'm killed. Okay, but I think if I am optimal, I would choose to be killed as early as possible. Okay, so the optimal solution here for Pac-Man is to go to the right and be killed after one step. That doesn't look any logical in the beginning, but if you think about it, Pac-Man is trying to maximize its gain. The gain will be much less if Pac-Man will stay more time, and he will lose anyway by being killed. But it's better to be killed as early as possible to lose less points. That's only if we assume that the opponent is optimal. Okay, so what will happen here is the following. You'll see here that, yeah, so Pac-Man will go right, okay, and immediately will be killed by the ghost. Okay, and that will be better for him than moving left and being killed after 2 or 3 steps, which means losing more points. Okay, so that's the thinking if I know that the opponent is optimal. Now, if I know that the opponent is not optimal and might not take optimal decisions or the rational decisions, then I should take my chance. I would say, okay, let me go left, hoping that this ghost is not smart enough and might go down instead of going up. Okay, so if this is 50-50 chance, I might have hope to get to eat these food items before being killed. So let's run it with a non-smart ghost and see what can happen. Of course, if we run it multiple times in actual game, it will have different outcomes. But you will see that there is a chance to survive. Okay, so moved left, the ghost moved away. Of course, this is very stupid ghost, but there was a chance to get to the game without even being killed. So that was good for Pac-Man. If we run it again, maybe we'll have a different outcome, but there is a chance for getting something like this. So the point here is that the strategy of the agent will be different knowing something about the opponent. If I know that the opponent is optimal, my strategy will be different than my strategy if I know that the opponent is not optimal. With that, I think we ran out of time. We'll inshallah continue on Sunday, inshallah. Just quick announcements. Since I postponed the project to Friday, the quiz was supposed to be on Sunday. I will move it to Tuesday to give you more time, and also to start working on the homework as a good preparation for the quiz. And the quiz will be on Tuesday, and I hope that also will be good preparation for the midterm exam. The midterm exam, as scheduled in the syllabus from the beginning of the semester, will be on October 4th, which is not Sunday, the coming Sunday, the following Sunday, which is like 10 days from today, inshallah. Okay, so watch out for your deadlines. You have a project tomorrow if you didn't submit. Many of you, by the way, submitted, maybe hoping for the bonus, playing against the optimal agent here. And so the project might be tomorrow. Quiz will be on, inshallah, Tuesday. Homework will be on Wednesday. So I urge you or recommend you strongly to do the homework early so that you will be prepared for the quiz, and then inshallah the midterm exam will be on Sunday. Hope the best for everyone. Talk to you inshallah on Sunday. Assalamu alaikum wa rahmatullahi wa barakatuh.